Hi, I'm Lin Ma from Carnegie Mellon University, and today I want to discuss MB2, a decomposed behavior modeling framework for self-driven database management systems. So database systems are essential for data-driven applications, but they are also becoming more and more difficult to manage given their growing complexity. The self-driven databases aim to address such challenge by autonomously optimize all system aspects such as indexing and knob tuning without any human intervention. So in our previous work, we have proposed a self-driven database architecture drawing some inspirations from self-driven cars. So our architecture first has a workload forecasting component that predicts the future workload that the system needs to optimize for. And second, a behavior modeling component generates models that estimate the behavior of self-driving actions, such as the cost and benefit of creating an index. And lastly, an action planning component decides what actions to apply given the workload forecasts and the model estimations. And today, I want to discuss our design on the second behavior modeling framework. So we think that behavior modeling is really a fundamental step towards building a self-driving databases. So to be slightly more specific, the input of behavior models are the forecasted workload in the future and a candidate self-driving action that the system may apply, such as building an index. Then the outputs are the cost and benefit estimation for that action on the specific workload. This could include how long this action takes, how this action helps improve the query latency, as well as the changes in resource consumptions. Also, to further motivate the necessity of behavior models, here I'm showing you an example experiment where we remove an important secondary index from the TBCC workload and then create this index back as a self-driving action with two different choices that use a different number of created index threads. So we start the workload with no secondary index, and you can see that the query latency at this stage is relatively high. Then we apply the create index action at around 50 seconds. We can see that right after the action starts, the query actually becomes slower because the index creation is competing resources with regular queries. And then using 8 create index threads has higher impact than using 4 create index threads because of more resource consumption. But then the index creation finishes much faster with 8 threads, so the queries become faster earlier. We think the ability to accurately predict the effects of those actions is critical for robust and effective control of the self-driving database. But there are quite some challenges to do this. The first is that database systems are pretty complex software. And if we want, for example, to use a single monolithic ML model to capture all aspects of the system, including all types of workloads and all these possible actions, the model can be very high dimensional with easily hundreds of dimensions. And this will subsequently require lots of training data to train and also difficult to debug. And secondly, in multi-core environments, actions and queries can also run concurrently. So the models also need to capture all kinds of interference between concurrent operations, which can further increase the number of possible inputs to the models exponentially. And next, it can also be pretty expensive to collect training data for certain database operation. Right? For example, if you want to know how much time it's going to take to create an index with 10 billion rows, well, getting that single label may already take hours. And lastly, for the practical applications of self-driving databases, these models should also have good interpretability, debuggability, and adaptivity. Of course, there are existing methods to build database models, which roughly fall into 2 categories. The first are the analytical models, where the developers write mathematical formulas to characterize the database component's behavior. And these models don't really need any training data, but typically require an onerous design process from the experts. And they are also difficult to adapt. For example, we cannot use the models developed for MySQL in our CMU DBMS. And then another category is ML model, which can be automatically derived by ML algorithms given some feature engineering and training data. So they definitely need a less manual effort and easier to adapt. But most of the existing ML models only focus on single query execution, which ignores other database components as well as the concurrent interactions among them. And furthermore, there's a lack of principled training data generation framework for those models. So typically the models are just trained with data generated from one or few canonical workloads, but there are results show that these models trained that way may not generalize well to new databases. Right? Now, we present an offline framework that sits in between analytical models and ML models and addresses the earlier challenges to generate behavior models for self-driving databases. So at a high level, our framework model 2 or MB2 first uses a set of specialized runners to fully exercise each database component to generate sufficient training data. And we wrote those runners with customized SQL queries on synthetic datasets. The runners use a lightweight metric system to collect the data and then send to a training framework to train two types of behavior models, namely a set of operating unit models to capture the various database components' behavior, and then another interference model to estimate the impact of concurrent operations. And an important property of these models is that they are workload and dataset independent, which means that the system only needs to train them once offline and then can apply them to any dataset or workload online. So now I'm going to do a little bit more details. First, the core idea of MB2 is to decompose the complex DBMS functionality into small and independent operating units, or we call OUs, to model separately. The main benefit of this approach is that each model is low dimensional, does not require a huge amount of training data to train, and also are friendly to interpret and debug. So now, to give an example, we decompose the noise page DBMS, where we implement MB2 to around 20 OUs, including, for example, building hash tables or creating indexes. And then each OU model has a specific set of input features that represent how much work this OU is going to perform. And these features can be different among different OUs. And these features may also include the database configuration knobs that impact the corresponding OU's behavior. For example, the OU model for serialized log records may contain the log serialization interval. But then all of those OUs share the same set of output labels, which include the OU completion time and different resource metrics for CPU, I/O, and memory. Then at the inference time, the self-driving database just sums up the predictions for all these small OUs to estimate the behavior of the entire system. So to be more specific, we classify all the OUs in a DBMS into three categories. The first is what we call a singular OUs, for which the OU model just predicts the behavior of a single OU invocation, such as building a hash table. And most OUs in our system belong to this category. The second category is what we call batching OUs, where the OU model predicts the behavior of several OU invocations together in a fixed time window. So this is mostly for the database maintenance tasks that perform periodically, such as serializing log records. And for those tasks, the amount of work to perform in each invocation is dependent on how much work is left from the last invocation. So it's a little bit difficult to predict the behavior of just one single invocation. And lastly, there are also a category of contending OUs, where the internal synchronization mechanism of that OU may affect the OU behavior. And for those OUs, we also include the contending information in their model input feature, such as the degree of parallelism for a parallel created index. Again, to give a specific example here, the build hash table OU will just have the number of rows, number of columns, column sizes, estimated cardinality, and the related knob that impacts the hash table creation as its input feature. All right. So to collect the training data for those OUs, for those OU models, we use a set of specialized runners that sufficiently exercise each OU through SQL-based synthetic benchmarks. So as illustrated here, each OU is paired with an OU runner to enumerate various possible inputs for that OU. For example, the hash table OU runner uses a set of customized workloads to exercise the hash table building with different number of rows, type of columns, and cardinalities, etc. to get the labels. And we use a decentralized metric system leveraging thread local storage to collect these features and labels with low overhead. And after that, a robust training framework searches over a wide range of canonical and state-of-the-art ML algorithms to find the best ML model for each OU. And we found in our experiment that for the scale of our OU, as well as the amount of training data we have, a gradient boosting machine typically performs the best. And another important thing I have mentioned is that it could be pretty expensive to collect labels for certain database operations. Right? For example, a build hash table, sort, or create index may need to process billions of rows. So to address this, we leverage one observation inspired by a previous work on query execution modeling, which is that For many database operations, or we call OUs, they have known complexity based on the number of tuples processed. So if we fix all the other input features, but the tuple number, and then we divide the output labels for these OUs by their corresponding complexity, then we sort of get a per tuple output labels that would eventually converge to a constant when the tuple number gets large enough, right? So we only need to collect labels for the OUs with a number of tuples up to this convergence point, which we found is usually below 1 million based on our experiments in our system. So with this approach, it takes roughly 10 hours to collect training data that exercise all the OUs for our noise-based system, which we think is an acceptable overhead if you want to build a self-driving database. So now I will present the model generalization results in a single-threaded setting. So we evaluate both OLTP and OLTP OLAP workloads, and we always use the same set of OU models generated offline for MB2. So for baseline, we compare against a state-of-the-art technique on query execution modeling called CubeNet. However, as mentioned earlier, CubeNet, like most previous methods, they don't really have a training data generation framework. So to simulate a production setup, we train CubeNet on one of these workloads and then evaluate on others. Now, here are the results. So the lower the bar is, the smaller the errors are, and thus the predictions are better. So from this, we can see that if we evaluate the prediction of the two methods on the workload CubeNet trained with, then CubeNet performs similar or better than MB2 because that's the workload that CubeNet is trained on. And the CubeNet has some specialized model structure to capture the workload pattern. But then on the workloads that CubeNet does not train with, MB2 achieves significantly better prediction. And the main reason for this is MB2's decomposed framework that generates sufficient training data to model each OU accurately. And I think we also learned an interesting lesson from this, which is that when in many cases we try to apply machine learning for databases, it may be super beneficial to jointly considering the models with what training data you really have for them. But now I want to talk a little bit about how MB2 performs so far in an end-to-end setup. So for this, we are going to primarily looking at how well MB2 predicts the changes in database query latencies if the system applies certain self-driving actions. And because eventually the self-driving database needs that information to make decisions. So we simulate a daily transactional analytical workload cycle where we alternate the workloads between the TBCC and TBCH workload. So we shorten the entire duration to 2 minutes to accelerate our evaluation. And in this experiment, we assume that the workload forecasts and the candidate self-driving actions are given so that we can isolate the error of MB2's prediction. So I will save the specific workload stages and action details for the later. But the thing I want to emphasize here is that database systems in reality often execute in multi-core environments, right? And during this experiment, the database uses 10 to 20 concurrent threads on average. And in this case, despite the great single-thread prediction accuracy, our models always under-predict without counting the resource computation among concurrent OUs, such as the CPU contention. And especially during this period of time, when an expensive self-driving action is applied, the OU models under-predict significantly. So to address this problem or challenge, we introduced another interference model that captures this concurrent impact. And what the interference model leverages are exactly the resource consumption labels predicted by the earlier OU models. So to be specific, the input features of this model are some summary statistics of the OU model outputs for some concurrent OUs forecasted to run in the same interval, such as their sum, their mean, their variance, etc. And then the output labels are the adjustment ratios between the actual OU metrics and the OU model predictions due to the interference. And similar to the OU runners, we also devise a set of concurrent runners that exercise various kinds of interference among OUs to generate the training data. So to wrap things up, here I'm illustrating the full inference procedure of MB2. So for a set of OUs that are going to execute based on the concurrent workload forecast, as well as the candidate self-driving action, the OU models first predict the behavior of each OU as if they run in an isolated environment. Then MB2 computes the summary statistics of the resource computation among all these concurrent OUs. And next, the shared interference model takes the summary statistics as the input and outputs the adjustment factors based on the interference impact. And lastly, MB2 applies the adjustment back to the original OU model prediction and sums everything up as the inference result. Finally, come back to the earlier end-to-end experiment. Let's see how good MB2's predictive power is. And again, it's the same daily transactional and analytical workload with TBCC and TBCH. And we assume that the workload forecasts are given as an oracle planner that can pick self-driving actions automatically. Right? So we only focus on evaluating how MB2 predicts. So we first start the TBCC workload, followed by the TBCH workload. And we can see that during this stage, the core latency for both workloads are relatively high. Then the Oracle Planner decides to change an execution knob for the TBCH workload to improve the TBCH core latency. And MB2 accurately predicts such improvement. Later on, the Oracle builds an index for TBCC with 8 threads. And again, MB2 successfully predicts that the core latency becomes worse while the index is being built, but becomes much better when the index creation finishes. Right? And not only that, our decomposed framework also provides detailed insights with the predictions, such as how long this action will take, how much resources that action needs, and also which queries are improved or impacted by the action. So we believe that all this information is crucial for the self-driving database to choose appropriate actions automatically. So now to summarize this talk, first, we think that behavior modeling is a fundamental step towards building self-driving databases. And we propose a behavior modeling framework that generates accurate operating unit models for database components with specialized runners to provide training data. And the next step in our journey is to integrate our previous workload forecasting framework, as well as the behavior modeling framework we just discussed, into an action planning framework that would complete the self-driving architecture. And lastly, just want to mention that all of these are developed in our open source noise page DBMS, which you are welcome to check out. And with that, thanks for listening and happy to answer questions.